work from the previous set 1 through 12. I'm happy to take any questions at this time. So I'll give you a minute to kind of look things over. What the heck just happened here? Yeah, Landon? 15. Okay. So here it says use a function grapher, aka your graphing calculator, to identify and classify all local maximums and minimums. Round your answer to the nearest hundredth. So fire up my graphing calculator here. To graph anything, I'm going to go to the y equals menu, clear out what I had in there, and then I'm going to just type in the function that's for number 15 as it appears on my sheet of paper there. So just like we did last time. So that's good there. I'm just going to hit graph because I know the window that I used was last time was still that -10 to +10 window, so that should probably still be good. Does indeed appear so. So I see a local max here and a local min here. So I just need to determine the coordinates for those 2 points. To do that, I'll press second and the trace button, and I'm going to use the maximum minimum commands. The point furthest to the left was the local maximum. That's the one I'm going to choose to find first. It doesn't really matter which one you want to do first. So it asks me 3 questions, left bound, right bound, and guess. So the first thing I'm going to do is move my cursor somewhere on the left side of that maximum. So like over in that area somewhere. And then press enter. Then it asks for right bound. So I'm going to move my cursor somewhere over here to the right of that maximum. That looks good. I'll press enter. Guess doesn't matter. And so I would say my answer here is -0.09, comma 2.05. Is that cool? And then I'll do the same thing for the minimum over here. So second trace. Choose the minimum command. Left bound is going to be somewhere on this little section there. So I'll just move my cursor. That looks good. Press enter. And then the right bound is going to be something over here. That looks good. Press enter. Guess doesn't matter. And so my other one is 1.20, comma -1.22. Does that feel okay, Landon? Okay. Those of you guys that just kind of wandered in, did you guys check in at the office already?
Yeah.
Okay.
I said you were not.
That's fine. I'm just double checking in case I have to update my attendance. But if you checked in, they'll handle it there. So, Victoria, 17. Okay. So the same directions here. So I'll do x times, and then the square root of x minus 1. And again, I'm going to just keep that same window. I think it'll probably be fine. If it's not, I can always go ahead and change it. So there's that. Now if I look at this, where does she go? I noticed that the graph starts right here, and then it just like seems like it just kind of continues up forever. So there is one minimum, and it's the start of the graph. That is the overall lowest point on the graph. Is that okay? Maybe it's a little easier to see if I do this. So I just turned off the XY axis. So we can see there is like a lowest point on the graph. It's basically like the beginning of the graph here. So whatever that point is, that'll be the absolute minimum. And that's also technically a local minimum, right? So to figure out that point, we'll turn the axis back on before I forget. I can realistically probably just look at it here, or I can use some common sense. If I look at my function, because of the square root there, the smallest x I can put in there is going to be the one that gives me a 0 underneath the square root, right? Because I can't square root anything less than 0. You buy that? And hopefully it's pretty clear seeing there that value would be 1, would be the smallest x I could plug into that square root. So you guys buy that. So the x coordinate is 1, and when I plug that in, the y coordinate I get then is 0. So 1, 0 is the coordinate there for that. Happy with that, Victoria? Cool. Anybody else? Yes, Jane. 18, okay. So I'll just get rid of this. I have x times the absolute value. So if you don't remember from last year, the way you get the absolute value symbol on your calculators, you have to press the math button here that's right below the green alpha button. And then you'll need to go over to the number menu. And it's this first command, ABS. And I'm guessing that was at least a part of the issue, right, Jane? Okay. And that's fine. So we got it typed in. I'm going to just go with this same window I've been using. If I can't see something, I'll change it, but I think it'll probably be fine. So I do that, and this is what I get. Now, I would suspect here that, or it's possible that there is no local maximum or minimum here at first glance, but I can't really tell what's going on real close to the origin there. It's possible that it does like a little doop or something in there and I just can't see it because I'm zoomed out too far. So I'm going to change my window and take a closer look. So maybe I'll just go from -1 to +1 on the x's and y's, and just kind of see. I'll change my scale to be 0.1 so it makes sense when I look at it, and just kind of see what's going on. You could also choose the zoom. You could use the zooms to just zoom into that area also if you wanted to. I usually like to change my window manually. So if I do that, aha! There's definitely a maximum and minimum hiding in there. I just wasn't zoomed in enough to see it. Okay with that? And again, I didn't know that those were going to be there, but because the question was asking me for maxes and mins, I didn't see any. I want to make sure. So the spot where they could have possibly been would have been that spot near the origin. So I just kind of zoomed into that spot to make sure that either it was just continuing to go and there's no hump or valley in there, but I found them. So now I can just use my calculator as I had before. So second trace, and then I can use my max and mins. I'll do the maximum first. So I have a local max here, so that where I'm at is a good left bound. And then over here is a good right bound, and I guess so 0.25 comma 0.13 would be your maximum rounded to 2 decimal places. And then my minimum, doing the same thing. Left bound looks good there. Right bound looks good there. Guess doesn't matter. About 0.50, comma. Now look at this number that's here. At the end, notice that this is E -6. What does that capital E followed by -6 saying? That's the calculator's language for scientific notation, right? Excuse me. So that's 0 point and then 5 zeros and then a 1, 2, or 1, 1, 2, yada, 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 right? If I round that to 2 decimal places, what am I really getting? 0, right? I'd have 0.00 or just 0 at that point. Is that okay, Jane? Victoria? Sure. And again, the window that I use doesn't have to be the same window you used. All you need is something where you can see, was there actually some max and min stuff going on in that spot? You know, so I just picked, instead of going from -10 to +10 on the x's and y's, I went from -1 to +1. And the scale doesn't really matter. I just changed it so I'd have some tick marks on my graph. The scale is just how far apart, like the little tick marks, the hashes are on your axes. So they don't really matter. They don't affect the graphing. But if I was going to try to, I didn't know if I was going to get it the first time. And so if I'm like, oh, I see like there's a little something in there, it gives me a better idea of like how much, what should I reset the window to a second time, so I'm able to get a better picture. If I could be like, oh, okay, like, so that's like 7.7 should get it, and then like 0.2 or something, you know what I mean? It would give me a better idea. But in this case, it wasn't necessary. Are you good with that? Okay. Cool. Shan, were you having a calculator problem? Did you get it sorted? No. Okay. Great. Anybody else? Again, you can ask about 1 through 12 still if you want to, or not. That's fine. Are we good? Okie dokie. I need sections here of chapter 1. Today we're going to start in on section 5, which is about symmetry. And for this class, we'll talk about 3, and again, okay, back up 1 second. So symmetry is another descriptor for a function, right? Some functions may have one kind of symmetry, they may have another kind of symmetry, and some functions have no symmetries at all, but it's another descriptor of a function, just like increasing and decreasing was a descriptor for functions. Symmetry is another sort of descriptor. In this class, we're going to be responsible for 3 types of symmetries. So the first one is called symmetry with respect to the x-axis. Now that phrase, with respect to, is a common mathematics phrase. I'm going to abbreviate it as WRT. You're free to use that abbreviation as well. You don't need to if you don't want to, but that's the abbreviation that I'm going to use. So an example of something, or a graph that has symmetry with respect to the x-axis, would be something like this. And when we say symmetric with respect to the x-axis, what that means is if I take the part of the graph that's above the x-axis and I reflect it across the x-axis, it should lie exactly on the part of the graph that's below the x-axis, right? That it's like a mirror image of itself. Does that feel okay to you guys? So what that's really saying then is if I have some point AB up here, down here I should also have the point A negative B. Right? Because if I reflect it across, AB should now become A negative B, right? Does that make sense to you guys? Okay. Or more generally, that the y-coordinate for x should also be, or the y-coordinate of x should also be the same as negative of the y-coordinate of x. So again, what we're saying is that if I take f of a, I should get b, and I should get negative b, which is what we're seeing in our picture, right? If I do f of a, I get the y-coordinate b, and I also get the y-coordinate negative b. What do you notice about this graph in particular in regard to things that we've been talking about? It's not a function, right? This would clearly fail a vertical line test. In general, graphs with this symmetry about the y-axis cannot be functions of y in terms of x. Okay? Which makes this maybe the symmetry we'll see the least of. So far, so good? Okay. Not surprisingly, if I have symmetry with respect to the x-axis, I can also have symmetry with respect to the y-axis. So what that'll look like is something like this. Where again, what we're saying is if I take the right side of the graph and reflect it across the x-axis, I should get exactly the left side of the graph. Everybody's okay with that? That there's basically now the mirror, instead of being the x-axis, is the y-axis. What this is saying then is if this is the point AB, this would need to be the point negative A, comma B. Or in general, that f of x needs to equal f of negative x. Right? The y-coordinate for A was the same as the y-coordinate for negative A, which is what we see in the picture, right? So in our function f, for any x-coordinate x, the y-coordinate for x should be the same as the y-coordinate for negative x. Everybody's okay with that? Okay, we have a special name for functions that have this type of symmetry. They are called even functions. Oops. There's an N in that. And more often than not, that's the term we use rather than symmetric with respect to the y-axis. We just say, oh, this function is even, rather than saying this function has symmetry with respect to the y-axis. Mostly because it's less words. The third type of symmetry, and the last type of symmetry we'll talk about in this course, is called 180-degree point symmetry. I'm abbreviating point as PT with respect to the origin. So with the 180-degree point symmetry, what I can think of is if I have some point and I like tie imaginary rope from that point to the origin, and then like spin that rope 180 degrees, I'm going to end up on the other part of my graph. So with respect to the origin is kind of telling us where the pivot is for the rotation, and the 180 degrees is we're spinning that, rotating that far where the pivot is at, in this case, the origin. So in general, if this is the point AB, this is the point negative A, negative B. Or we can say that f of negative x is equal to negative f of x. The y-coordinate of negative a is the same as the y-coordinate of a, except we have to make it negative, which is what we're seeing there. We call these functions, we have a special name for these, we call them odd functions. Again, 180-degree point symmetry with respect to the origin is a bit of a mouthful. In practice, we would just say, oh, that function's an odd function, rather than that it has 180-degree point symmetry with respect to the origin. Like anybody else, mathematicians make up their own slang and shorthand and abbreviations and everything else. Lily?
Why is it f of negative x is negative f of x? Shouldn't it be f equals x through f of x?
Well, let's do this in terms of A's and B's, since those are the points that we drew, right? So we're saying this is true, right? So f of negative A is negative B. F of A is B, and then negative of B is just negative B. Is that okay? So like, f of negative A is negative B. F of A, ignoring the negative sign, is B. So that's what it's saying. Is that the x-coordinate of A, or the y-coordinate of negative A is the opposite of the y-coordinate for positive A. Is that okay?
Yeah. Thanks.
Yeah. So just kind of maybe not the most intuitive way of writing that relationship, but it turns out this is kind of the most practical way of writing this relationship for what we're going to use this for. Okay, so up until this point, we've given like a visual kind of definition of what we mean by these three symmetries, right? If we give you a graph and you look at the picture, reasonably you could identify what type of symmetry it is. Everybody agree with that? Again, that's not too difficult. There's no real calculation to do. It's just kind of using your eyes and visualizing in your head. There's not much I can do to, to show you how you're doing that visualization other than kind of talking through what I'm doing or what I'm picturing in my head. We also gave you an algebraic definition. So the algebraic definitions in these cases were always these relationships. And that's the part that we're going to be using to do the problems. So we'll do a couple of examples doing this. So don't get too scared when you read the direction. It says prove. The proof here is not like a geometric proof where you're doing two columns and using theorems. Okay? The proof here is just using our algebraic definitions. So these are the algebraic definitions we're going to be using to do this proof. So maybe before we even get started, it would make sense to graph my function and just take a look at the picture so I have an idea of what I'm going to be proving, whether I know, so I know whether the answer should be odd or even or neither, right? Everybody's okay with that reasoning? So I'm just going to punch this in real quick and take a look at the picture. So x to the fourth plus 1, and then I'm going to do zoom standard because I was monkeying with the window on that last homework problem that we were doing together. So if I look at this, what type of symmetry am I seeing? Even, right? Because it's symmetric with respect to the y. Everybody's cool with that? Okay. So let's go ahead and do the proof then. So the definition for even is written here. So this is what I need to show, is that f of negative x is equal to f of x. So to do that, I'm going to figure out what f of negative x is, and hopefully it turns out to just be x to the fourth plus 1. Everybody good with that plan? Okay, so when I plug something into a function notation, that means that it's going to replace all of the x's with whatever we plugged in. So I'm going to replace all of my x's in my function with negative x's. Everybody's okay with that? Okay. So I have negative x to the fourth. What that really means is I have negative x times negative x times negative x times negative x, right? 4 negative x's multiplied together. When I multiply 4 negatives together, what do I get? A positive. When I multiply 4 x's together, what do I get? X to the fourth. Everybody agree? And notice now that this is the same as this. You guys agree? So I know it's equal to f of x, right? That's what we said f of x was in the very beginning. That was what was given to us in the problem, was that it was equal to x to the fourth plus 1. So what I've shown is f of negative x is equal to f of x. So by definition, this is an even function, and I'm done. Is that okay? Again, if I did something too quickly, or you need some more explanation, or you don't get something, stop me, ask a question. We'll do our best to fill in whatever it is that we're missing and try to make it so it's a little bit more understandable. Everybody's okay? Let's look at another example. Let's say now we have g of x equals 2x cubed plus 3x. Oh, that's embarrassing. Just like before, I'm going to go ahead and do the same thing. I'm going to start by just looking at the graph so that I have a good idea of whether I'm looking for something that's odd or even. It helps to have an answer for a question like this before you're going ahead and proving it, right? Helps you figure out if you have any error or anything like that. Okay, so here's my graph. Not real exciting. What type of symmetry do we see here? This looks odd to me as well. Do you guys agree? Okay. Let's go ahead and start the proof then. So again, here I'm looking at an odd function. Again, I'm going to start with f of negative x. Well, I guess g of negative x. My function is named g in this case. So when I do g of negative x, I'm going to replace all the x's in g with negative x's. Everybody so far so good? If I have negative x cubed, that's negative x times negative x times negative x. When I multiply three negatives, I get a negative. When I multiply three x's, I get x to the third, right? So that first piece is going to be negative 2x to the third. And then 3 times negative x is just negative x. Or negative 3x. Yeah. So far, so good. Worth pointing out to us that this and this are not the same. So I know that it's not even. How are they different? The signs are different, right? The one in blue has negatives, the one in black are positive. So I'm going to go ahead and factor off a negative sign. So when I factor that negative sign off, the 2x cubed becomes positive, and the 3x becomes positive. And this piece is now equal to that piece. Oops. And because I still have that negative sign in front, I can write that as negative g of x. Everybody's okay with that? So what I have is I have negative, or g of negative x equals negative g of x. So that's the definition of odd. Is that okay? Again, if I'm going too fast or you need some more explanation or you're like, I just don't get it, can we talk through it again? Or I'm missing something, that's fine. Let me know. Landon?
So how did you get it so it's negative g of x?
Okay, so the piece in yellow here, you see that? That's not g of x. We established that, so I know it's not even. So to check if it's odd, I'm going to factor off a negative sign. So there's my negative sign that I factored off. When I take that negative sign out, the 2x cubed becomes positive and the 3x becomes positive. That part in green is g of x. I still have this negative sign here, so I have negative g of x.
So even if like the graph looks odd, so check for it.
I was just making that observation along the way, just so that you can see that you can't be even and odd. I know that maybe is you wouldn't think that you could be both, but I was just kind of illustrating that along the way to get to odd, you're going to pass even. You know what I mean? So it's really the same start for both of them. Does that make sense? So yes, this part wasn't necessary, but I wanted to show how, because when we do a neither, that's what we're checking, is that it can't be odd and it can't be even. So as long as we're kind of starting this, I figure it would just, you get it. All right. Our last example here . Again, let's start by plugging this into our calculator and looking at the picture. Often helpful to know what it is that we're looking for. Okay, so I could see part of the graph show up here, but that's not very helpful to me. So I'm just going to make the graph a little bit taller. Instead of going to a y max of 10, I'll make the y max 50. And actually, let's change that scale too, so it's a little bit less of a block there. Now look very carefully. Is this an exact reflection? No, you can see there's a little bit more of the graph on the right side than the left side. So this isn't even. Everybody agree? You can see why? It's a little subtle, but if you look closely, you can see there's more graph on the right side than the left side. Agreed? Definitely not odd, so this one should be a neither. You guys agree? To prove something is neither, we're going to show that it's not even and that it's also not odd. So we'll start the same way with h of negative x. I'll plug in my negative x's. Negative x squared is negative x times negative x, which is just x squared. Everybody's good? So I have 4x squared plus 3x plus 9. This is not h of x. So I know it's not even. Everybody's good there. If I continue on and try to show that this is odd, I would need to factor out a negative sign. So since each one of these terms were positive, when I factor out a negative, they become negative. Right? Just factoring a negative sign makes all the terms switch sign. And this stuff is also not h of x. And because I have a negative sign out front, obviously it's not negative h of x. So I know it's not odd. So it's neither. It can't be even, it can't be odd, then that's neither type of symmetry. Is that okay with you guys? So Mr. Kulik, you graphed all of these to tell if they're even and odd. That's great, right? You know, it's going to be even easier than that. I can just look at these equations and tell if they're even or odd. Let me explain how. So the sum of even functions is going to be even. The sum of odd functions will be odd. The sum of even and odd functions is going to be neither. For polynomial functions, a monomial with even degree is going to be an even function. A monomial with odd degree is going to be an odd function. So if I go back and I look at these, each of these were polynomial functions, right? So if I go back, the degree for x to the fourth is even. The degree is 4, right? The degree is the sum of the exponents on the variables. In this case, that's 4. There's just one exponent on one variable. What's the degree of 1? Are there any variables? So what's the degree then? 0, right? There's no exponent or no variables. So it's like you have an x to the 0 there. Remember, anything to the 0 power is 1. So degree 4, degree 0, both of those are even, so I know this will be even without having to graph it. Now, do you need to know that to do this? No, but it saves you a couple of minutes of typing stuff into your calculator because you can just look with your eyes and know what it is that you're looking for. You don't have to graph it to tell if it's going to be odd or even. If we look at g of x, the degree on 2x cubed is 3. That's odd. The degree on 3x is 1. That's odd. Odd and odd is odd. Everybody okay? If I look at h of x, the degree on 4x squared is 2. That's even. The degree on negative 3x is 1. That's odd. I'm going to stop right there because I have an even and an odd. That has to be an either. I don't even care what anything after that is. Is that okay? Again, not necessary that you have that information or you use that information, but it might save you a little bit of work in terms of having to get stuff into your calculator. Okay, what do we got here? Let's stop. This feels like a good place to end. That's the end of a section. It's Friday.